Okay, so you have a standard deck of cards, and it wants us to find each of the following. So, one card is drawn. Find the probability that is ace or red.
So the formula I would use.
I'm gonna give you a hint. You don't need a formula yet.
You just find the you just like find P ace and P red, right?
Yeah, and then remember, 2 of your reds are also going to be an ace.
Okay.
So basically, you need all your red, because there's 2 aces already included with that. And then you need the 2 aces that are black.
Okay, so for P ace, it would be so there's 4 aces. So it's like 1/4.
That's just the probability of 1 ace out of the 4 aces.
So it has to be ace or
Not and, just or.
red.
So it might be easier to look at it like this. So we have, we're going to have black and we're going to have red. So how many aces total exist in a deck of cards? 4. How many total red cards are in a deck?
26.
Okay, but how many of those are aces?
2.
So 24, and it's going to be the same thing for black. So I'm adding up the probability that it's an ace or red. So I want red plus ones that are just red plus the ones that are aces. So it's just 28 out of 52. And then, just to save time, that's equal to 0.5385. Normally, well, I don't know. I don't ever have a set amount of decimal places for these because some of these answers end up being like 0.000 something. So I usually just say go to like 2 like actual numbers. So, all right, the next one. 2 cards are drawn without replacement. So that means once they're taken out of the deck, they're gone. Find the probability that both cards are aces. So, how many aces are originally in a deck? Okay, so we start out with 4 out of 52. That's card number 1. So then, if you take that one out and you don't put it back, how many cards are left?
48.
Take the one card that you pulled out. How many cards are left?
54.
Okay, so times, if the first one you pulled was an ace, what is the second one? Or how many aces are left that you could possibly pull? 3. And then we multiply. So 0.0045. Okay, the next one. 5 cards are drawn without replacement. Find the probability that all are spades.
So there are 13 out of 52 spades. If you take out 5, that'd be 47. Something over 47. What?
You're taking out 5 cards. So you've pulled the first card. So you're down to 51 cards left.
So you gotta do it like numerically.
So you're down, you've taken one out. So you're down to 12 over 51.
That's insane.
Then you're at 11 over 50. Then you're at 10 over 49. And then the last one is 9 over 48. And you'd multiply all those together. which ends up being 0.000495. That's what I'm saying. These problems are very weird. They're fun. I like them, but they're weird. Because you have to think, you're taking one card out, and they're saying that all are spades. So it's kind of like going back to, like the probability problems when we said, like, you had the bag of M&Ms, and it was like, you take one M&M, like, what color was it? Like, do you remember what I'm talking about?
Yeah.
It's kind of like that, where, like, I don't remember if we were putting it back in the bag at that point or not, but you take that one out, that one's gone. And if they told you how many were there to begin with, then you're just going to continually go down until you're either out or you hit whatever they want you to hit. One card is drawn. Find the probability that's a heart, given that it's red. So this would be the probability that it's red intersected with that it's a heart divided by the probability that it's red. So how many cards are red hearts?
30%.
Yep, 13. So that would be the top number. And then how many total cards are red?
26.
26. So that just ends up being 0.5. All right, so then the next one looks like a similar question. One card is drawn. Find the probability that it's red, given that it's a heart. So the intersection at the top is still the same. It's the probability that it's a heart now intersected with that it's red, divided by the probability now that it was a heart, because whatever's after the line is always what goes on the bottom. So the probability that is a heart. So that's going to end up being 13 over 13, which is just 1. All right, the next one. One card is drawn. Find the probability that's red or a face card.
So that's like the Jack King.
So you want all the reds and then the Jack, King, and Queen for the other two suits. So there are 26 total red. And then there would be, well, there's 12 total face cards. But if we've already accounted for the red face cards in the total red,
6.
yeah, so then there would be 6 of the Jack. I don't know why I always say Jack, King, Queen, but it's the other way. So we just add those two together. So that ends up just being 26 plus 6 out of 52, which ends up being 0.615. So with something where, like a deck of cards that you know how many of each thing exist, I will often just do the adding. I won't go through and make the Venn diagram and like split everything up. But when it's just like numbers thrown at you or like decimals that are already given to you, you kind of have to do the Venn diagram to figure out where the overlap is and stuff like that. All right, then the next one. One card is drawn. Find the probability that it's red and a face card. I was like, is that literally the same question?
So
So we're looking for the overlap.
okay, so P red intersected with this one. Is it divided by P red or P face?
It's just divided by the total number of cards.
Okay, so we divide by 52.
Yeah. So basically you're looking for how many cards that are red are also faces.
So now it'd be, so it's 26 reds.
But how many of those are faces?
And 6.
So that's all I care about. Because it has to be both. So the difference with this one and the one before was we wanted red or a face card. Now it has to be red and a face.
Okay.
So I don't care about anything but those 6 red faces. So this will be 6 over 52, which is 0.1154. All right, so then just these 2 rules. I know they're in kind of the notes, but just to have them here handy. The addition rule, think or union. Those are the 2 words that'll clue you in that you're using the addition rule. So the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersect B. So we've got to get rid of the overlap one time because it's occurred twice when we've added them together. So with that, get rid of overlap. Now that's in general. If A and B are disjoint, meaning there's no overlap between them, the probability of A or B, or A union B, is equal to the probability of A plus the probability of B. But we can, again, only use that if there's no overlap. So that was kind of the last section that we did before break. Now we're getting into the ones that are going to have overlap most of the time. And then the multiplication rule, we're thinking and. We're looking for intersection. Those are our clue words. So the probability of A intersect B is equal to the probability of A times the probability of B given A. And this could also be written as the probability of B times the probability of A given B would be another way you could write it. If we know that A and B are independent, then the probability of A intersect B is equal to the probability of A times the probability of B. Just trying to see if there was a spot to write conditional probability. If not, I'm going to write it on here too. Okay. I don't think there's anywhere for conditional probability to be written, so I'm just going to write it down here. But conditional probability is that the probability of A given B is equal to the probability of A intersect B over the probability of B, and that could also be written the other way. If you had B given A, it would be the probability of B intersect A over the probability of A. So whatever the second thing written is what goes on the bottom, and then it's just the intersection of the other 2 things. Let's go ahead and see if we can do example 2. Did you get all that?
Yeah.
Okay. All right, so employment data at a large company reveal that 72% of the workers are married, 44% are college graduates, and that half of the college graduates are married. Draw a Venn diagram to represent this situation. So, okay. So I'm gonna do M for married, and then C for college grad, and then the middle is obviously gonna be both. And then outside is that they're neither. So we're told, I always do the middle first because it's the easiest thing. It's what's given to you. So it says that half the college graduates are married. So that's going to be the middle chunk. So that's going to be the 0.22 because we're halving 44.
Where do you get 0.22 from?
So it says half the college graduates are married. So there's 44% that are college graduates. So I'm just taking that and halving it. So then, to find how many are just college graduates that aren't also married, I would need to do the 44 minus whatever the overlap is, which since it said half, we just know the other half is on the other side. So that's 0.22. So then it says 72% of the workers are married, but we know 22% of them are also college graduates. So how many are just married and not college graduates?
What do you say? It is 72% are married.
Yeah.
And it's 44 college graduates.
But of those college graduates, only half of them are married.
So it's 36. Or 0.36.
No. So we're taking the 72% that are married, and we need to subtract off the ones that are college graduates. So it's 72 minus 22.
0.5.
So, yes. And then we want the whole box to be equal to 1. So I need to see how many are neither. So we add them up. So that's, what is that, 0.44 plus 0.5. So that's 0.96. Or wait, no, wait, 0.94. So 0.06, there we go, are neither. And when you do set up a Venn diagram, like early on, you pretty much will be able to answer all your questions from that. So what is the probability that a randomly chosen worker is neither married nor a college graduate? Well, because we did our diagram, we can see that it's 0.06, because everything outside of it. What is the probability that a randomly chosen worker is married but not a college graduate? So that means that they're just married. They can't be in the overlap. So that's 0.5. And what is the probability that a randomly chosen worker is married or a college graduate? So you can either, once you have your Venn diagram, add up all these numbers and just give that number down here. Or you can actually use the formula, the probability of A plus, or well, here, I'll do this. The probability that they're married plus the probability that they're a college graduate minus the probability of married intersected with a college graduate. If you did that, you're using the original numbers you were given. So 0.72 plus 0.44 minus 0.22, which would give you the 0.94. Or you could have just added up the numbers in the diagram and get it as well. But this is just, I just was going to show it using the formula. So if you didn't have the diagram, that's how you would find it. But sometimes that gets to be confusing because people are like, oh, well, I have the diagram, so it's just 0.5 plus 0.22 minus 0.22. Well, that's not once you have this already divided, the formula doesn't matter anymore. Because the only thing the formula is doing is subtracting off the overlap once, because it would be included twice. I thought you threw that away.
Wait, you said it's 0.06, right?
Yeah. So these two numbers, so the probability that they're married or a college graduate plus the probability that they're neither should add up to 1.